Welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll learn about how a single GPU can tackle multiple tasks simultaneously. A GPU, which stands for Graphics Processing Unit, is a special chip that helps computers process images quickly. GPUs are commonly used in activities like gaming, video rendering, and graphic design, where it excels at handling lots of tasks all at once. This ability is especially handy for tasks such as smoothly rendering detailed 3D scenes. We'll employ one GPU to execute matrix multiplication within our Fortran program. The GPU has a lot of small computing units called cores. For example, the P100 GPU on our Axel nodes has 3,584 cores, and the A100 GPU on the A100 nodes has 6,912 cores. It's essential to understand that our Fortran program cannot directly execute on the GPU. Instead, the executable Fortran program must be initiated on a CPU core. The CPU core undertakes crucial responsibilities like managing system resources, coordinating data transfers between different components, handling system input-output, and performing tasks that may not align well with the parallel processing capabilities of the GPU. The CPU core is often called the host of the program, responsible for managing data transfers between the CPU memory and the GPU memory, as shown by the black arrow in the diagram. These data transfers are a critical bottleneck. The GPU is often called the device, and the CPU can transfer compute-intensive parts of the Fortran program to the device. This transfer process is known as GPU offloading. To compile our Fortran program, we need a compiler. The Intel Fortran compiler, iFort, does not support GPU offloading. Instead, we'll use the NVIDIA Fortran compiler, NVFortran, which is designed to work seamlessly with NVIDIA GPUs. To obtain the most recent NVFortran compiler, we'll need to install the latest NVIDIA HPC software. I've simplified this process by creating an alias NVHPC in my .bash rc file. Similarly, I've created another alias Intel to easily load the latest Intel Fortran compiler. I can utilize my new alias NVHPC to load the NVIDIA HPC software. By using the command module list, I can obtain additional information about the loaded modules. To explore detailed tutorials on module load and accessing software on Saga, you can find comprehensive information in the HPC onboarding videos available on this YouTube channel. The onboarding videos provide in-depth explanations and practical examples across various topics. You can access information about the NVFortran compiler by entering man NVFortran at your command prompt. Using this command will show you the manual for the NVFortran compiler in your terminal. We'll cover more about compiler options later. I've created a Fortran program to offload matrix multiplication onto the GPU. We'll examine its performance using a matrix size of n equals 16,384, which is double the size we analyzed at the end in the Fortran optimization video. We'll use a method that involves applying the do concurrent instruction, which was introduced in the Fortran 2018 standard. Essentially, we'll create a single do concurrent loop over the triple nested do loop for matrix multiplication. This do concurrent loop runs only once, leaving the GPU offloading to be handled by the NV Fortran compiler. It's worth noting that this program maintains the original loop sequence of I, J, and K. We'll save this version of the program with a file ending equal to 1. To handle compiler options and other tasks, I've created another Python script. As you may have noticed, I prefer using Python scripts to streamline many Linux command tasks that would otherwise require manual typing in the terminal. I find this approach more efficient and it helps me keep track of what I've done. Again, we'll make use of the OS and time modules. Our compiler is set as NV Fortran, targeting the NVIDIA P100 GPU installed on the Accel nodes. The variable GPU offload determines the method we'll use for offloading. Initially, we'll start with the do concurrent method. The file ending suggests that we'll be testing multiple Fortran programs using the do concurrent method. Specifically, we'll start by testing the Fortran program we've just examined. Additionally, we'll monitor GPU performance by setting the monitor variable to on. We're setting n to 16384, just like in the Fortran program. Then, we divide by 1000 to calculate performance in gigaflops. Additionally, we'll run the executable program 3 times to calculate the mean wall time. As we saw in the CPU billing video, the billing factor for the Accel nodes is typically 6. Therefore, we're setting the billing factor to 6 accordingly. The file name variable combines both the GPU offload variable and the file ending variable. The former specifies the GPU offloading method, as discussed earlier. The monitor variables are employed to track GPU performance. We've specified that we want to monitor GPU and memory utilization, along with timestamps. These performance metrics are saved in a file named monitor with a CSV extension, which stands for comma-separated values. Additionally, we calculate the total number of floating point operations. Since we divided n by 1000 earlier, this calculation yields gigaflops. We use particular compiling options to optimize performance on the P100 NVIDIA GPU on the Accel nodes. Specifically, for the GPU, we employ the specifications CC60 for the P100 and CC80 for the A100. In applying the do concurrent method, we utilize corresponding compiler options. Notably, our Fortran program runs on 1 CPU core and is then offloaded to 1 GPU. Consequently, certain options affect the CPU, while others influence the GPU. According to the NV Fortran compiler manual, the std_par option manages GPU offloading with the do concurrent method. By setting this option to GPU, we request parallel execution on the GPU. In this test, we're employing the fast optimization option, which impacts both the CPU and GPU. Additionally, the march option, affecting only the CPU, specifies it as a Skylake architecture to match our Intel Xeon Gold 6126 CPU. The do compile variable holds the compilation command, which is displayed in the terminal and then executed. Since we've opted for GPU monitoring, when monitor is set to on, the Linux commands shown above are executed. The for loop runs the program 3 times because the variable numRun is set to 3. We utilize the time module to measure the wall time and then display it in the terminal. We additionally calculate the total wall time using the cumulative sum method and then determine the mean wall time. The mean CPU time is calculated using the billing factor. This time represents the portion deducted from your CPU quota, as explained in the CPU billing video. Finally, we calculate the performance measurement in gigaflops per second. There are two metrics, one based on wall time and the other on CPU time. Both are displayed in the terminal, along with the mean wall and CPU time. We'll explore these different measurements in our future videos. It's important to note that with a billing factor of 6, the GPU performance should be compared with parallel computing on 6 CPU cores. This relates to multi-core computing, a topic we'll cover in upcoming videos. Before we proceed with any testing on the Excel nodes, we must update our Python setup script for interactive jobs. This means using the salloc GPU variable to request one GPU on the Excel node and increasing our memory request to 7 GB, since we're now using n equal to 16,384. However, we'll save the offload testing for our next video. I am looking forward to the next video, wishing you all happy computing in the meantime.